All right, good morning, everyone. Welcome to our Hydraulics of Backflow Detector Assemblies Types 1 and 2 webinar. I'm your host, Greg Jackman, the Specification Program Specialist here at Watts. We also have Andrew Sophia, our Product Production Manager, here as a technical support resource as well. Today's webinar is the next installment in our series of webinars geared specifically for you guys, our engineer, architect, and specifier customers.
Great.
The next slide there. All right, just to give you a little background up front in the series, we hold several of these webinars throughout the year. They cover a variety of topics. Our presenters are always our in-house and technology product experts, and thanks to our partnership with the American Society of Plumbing Engineers, ASSE, we're able to provide you with a 0.1 continuing education unit credit if you stick around for the entire webinar. After today, our next one will be on November 14th, where we'll be talking about our commercial rainwater system solutions. If you're interested in registering for that one, please keep your eye out for our emails. You can download this presentation deck from the Event Resources tab on the bottom left of your screen, and you click the link in this slide to register, or you can just reach out to me directly at gregory.jackman@wattsware.com, and I'll sign you right up. So with that being said, I'd like to introduce you to the presenter of today's webinar, Cameron Rappaport, our Backflow Product Specialist at Watts. He works with engineers to provide support in managing our backflow prevention product line, including new product development and training. During the duration of today's presentation with Cameron, the phone lines will be muted, but we encourage you to submit questions using the Ask a Question box at the bottom left-hand side of your screen. We'll then address them during and after the presentation. We also wanted to call your attention to the Event Resources box in the bottom left as well, where you can download the presentation deck. And then underneath that, you can take a survey to give us your feedback on this webinar. So with all that being said, let me pass it off to Cam to get started.
Great. Good morning, everybody. Let's start with some just about this course. Do our housekeeping. We'll get right into it. So this course is approved for ASSE CEU credits only. It is not necessarily approved for professional development hours for our PEs if you're on the phone. May or may not be accepted PE renewal. It's going to be kind of a case-by-case basis. But if you're a certified in plumbing design or a certified plumbing design technician, you can use this course towards your recertification. So inquire with your state to determine if it's eligible for PE renewal or PDH credits, but it definitely is an ASSE-approved seminar. All right, so our objectives at the end of this course, you're going to be able to understand some of the history and necessity of detector assemblies, type 1 and 2, the hydraulics of those detector assemblies, the benefits, so why do we have type 2, a look at the approvals, and then how to test and report on them. So we're going to go through our history of backflow, so then the basic hydraulics of the DC, DCDA, RP, and RPDA. Those are the type 1s. Look at the detector assemblies. What are they used for? Are they legal? And type 2, same questions. What are the hydraulics? What are they used for? Are they legal? Are they safe? Right? And then we'll get into questions, which you guys can submit as we go along. I might answer them while we do it, or if we're getting a lot of questions, we'll probably wait till the end. So let's jump in with some history of backflow. So backflow history really started at the 1933 Chicago World's Fair, where a plumbing cross-connection between the sewer and the potable lines in a building resulted in 98 deaths from dysentery, which is not a fun way to go. This made people realize that we need some sort of plumbing codes within the buildings to help protect public health. This led to the creation of a cross-connection board in Los Angeles and the establishment of the USC FCCCHR, which is the University of Southern California Foundation for Cross-Connection Control and Hydraulic Research. For obvious reasons, that's a big mouthful. We typically just call them USC. So USC published the first laboratory and field evaluation standards for DC and RPs in their seminal paper number 5 in 1948. And then this was then rolled out and recognized nationally as a standard along with ASSE in the 1970s. So here is the history of the backflow at USC. You can see in 1960 we got the first edition. We're currently on the 10th edition. They're working on the 11th right now. So what I'm trying to show here is that even though backflow preventers might seem like they haven't changed much, the codes and standards as well as the valves themselves have really evolved over the years. So in 1974, 2 years after the WATS 909 came out, if you can believe it, the USC 5th edition manual was released at 134 pages long. Did not contain anything on detector assemblies. In response to the industry, DCDAs were added in 1979. Then as RPs got more popular in fire application, RPDAs were added in 88. And in 2009, a full decade ago, Type 2 detector assemblies were added. So by this time, the 10th edition was almost 4 times as long as the 5th edition at 512 pages. So what I'm trying to demonstrate here is that even though a DC still seems like a DC, the codes have evolved, they've gotten stricter, and there is a new technology, the Type 2 bypass, which even though I'm calling it a new technology, is really a decade old. It's been in the standards for a full decade. So our most important question, why detector assemblies? Well, detector assemblies are there to help cover the non-revenue water and unmetered fire connections. So fire connections were among the last connections to add backflow prevention. In fact, in several parts of the country, they still don't have real backflow preventers. They use single checks. So when water authorities began mandating actual backflow preventers be installed, they wanted a way to detect loss of water in these unmetered connections. They're unmetered for a variety of reasons, one being that we've all agreed that we should put out fires and not have to pay for that water. The other is that the water meters would be one more thing in line to cause a pressure loss or something that could break. And the last one is that fire lines tend to be very large. A commercial building might have a 2-inch potable water line and a 6-inch fire line. 6-inch meters are very expensive. So water companies don't want to meter the connection, but they want to know if water is being used for something other than putting out fires. So they want to monitor it. If you're a glass half full kind of person, it's to monitor for leakage or accidental usage. If you're glass half empty, it's to monitor for theft since that water is free. So I don't know who would want to tap into a fire protection line for potable water because that water is pretty gross. So a couple more definitions. Definition of a cross connection. So a cross connection is a temporary or permanent connection between a public water system or a consumer's potable water system and any source or system containing non-potable water or other substances. So a fire system is a permanent cross connection, right? It's a permanent connection that's been created between the public water system and a non-potable system, which is the stagnant water in the fire sprinkler. The detector itself is another cross connection. It's a bypass around the backflow, so it's another direct connection between a potable supply and a non-potable system. It also has to be protected. So let's get into our hydraulics of our basic assemblies. So here we have our double check valve assembly. It's very popular in fire protection systems. The double check valve assembly can also be referred to by its ASSE standard number, which is 1015. These are for non-health hazard applications, which fire sprinkler systems are typically classified as. That basically means that the water in a fire sprinkler system is undesirable, right? It's usually probably going to taste bad, it's going to look bad, it gets all rusty, but it's not dangerous if you drink it. So that's a non-health hazard application. They're testable, so each of the assemblies has 4 test cocks, and it's typically tested annually. They can be installed horizontally or vertically, or in an end pattern like that gray valve on the right. One thing I like to mention is the reason these are called double check valve assemblies, and not just double checks, is that all testable backflow preventers are approved with the shutoffs. The shutoffs are a part of the assembly. They should not be removed. They shouldn't be replaced with a non-approved shutoff, or another really common thing we see is a strainer or a pressure reducing valve being placed between the shutoff and the backflow body, so you don't have to get another ball valve or get another gate to be able to service those. Most inspectors will fail if they see any of those things. Those shutoffs are there to maintain the integrity of the valve and allow it to be tested without interference. So here you can see a cutaway of a small diameter double check assembly. So there's a couple red discs in there. Those are the soft seat. They're up against a hard lip, which is your hard seat. Those affect the seal in those checks. Each check is designed to hold a minimum of a 1 psi pressure differential, which you can see here. So our pressure is dropping from 60 psi to 59 psi across that first check, and then 59 psi to 58 psi across the second. So remember, these are minimums. Often you'll see them higher. If you're a tester, if you've tested a lot of backflow preventers, you'll know that these being 1.5 psi and not 1 psi is very common. So here we see a cutaway of a larger diameter double check. So even though the check style is different, right, it's much larger. These are big clapper checks instead of the poppet checks you saw in the previous cutaway. Hydraulically, it operates largely the same way. You still have a minimum 1 psi pressure drop across that first check and the second check. Doesn't matter if it's a 1/2 inch or a 10-inch device. Oh, we have a question about describe how the double checks are being tested. Sure, when people are testing a double check, it depends on exactly which standard you test to. Up here in Massachusetts, where I am, we have the NEWWA. You might be using ASSE tests or the USCE tests or the TRIO test. But essentially what they're looking for is they're looking to make sure that that check is holding, or each of those checks is holding that 1 psi differential. So they have a differential meter, they hook it up, you bleed through some water, and then you're looking for it to settle at on or above 1 psi for each of those checks. Then there'll also be things like shut-off tightness tests to make sure no water is flowing that could interfere, but the heart of what they're testing for is the differential across those first two. Oh, we have another question in. A little off topic, but I'll address it anyway. How can anyone consider irrigation as non-health hazard? This is open to the environment and subject to chemicals, fertilizer, etc. Personally, I would say irrigation is a health hazard application, but it's debatable. Part of it is about, you know, for residential irrigation systems, what kind of costs and, you know, installation difficulties does the municipality want to impose on the consumer? But that's decided at, you know, the AHJ level, town, county, city, state. So unfortunately, you know, I can't just mandate that everybody uses an RPD. Anyway, back to DC. So we've looked at DCs. Let's take a look at the detector assemblies. So you notice it's very similar to a double check, but these are a different ASSE standard. They're 1048. You can see that unlike a simple double check, these are typically only available from 2 inches and up because they are for fire connections. You don't see a lot of small diameter fire connections. It also becomes very difficult to put a bypass on a very small valve. Otherwise, they're almost exactly the same as a double check with the additional of that bypass to monitor for unauthorized water usage. The hydraulics are a little bit different, so let's take a look. So here we have our DCDA-Static Flow, so zero flow. Now the first 2 gallons a minute have to flow through the bypass by code. In order for that to happen, we need stronger checks in the main valve assembly or weaker checks in the bypass. In this case, the bypass already has 1 psi check. That's our minimum, so we have to strengthen the checks in the main valve. So here you can see across that first check, the differential is now 2 psi. We're going from 60 to 58. Now over on the second check, it looks like there's no pressure drop across it, right? You have 58 psi on one side and 58 psi on the other. That check is not fouled. In fact, it is still a 1 psi check, but the drop across has been affected by the bypass. So if you imagine the last time water flowed through this valve, as demand dropped and downstream pressure rises, it'll hit 57 psi, which is our total static pressure drop across that first main valve, right? 2 psi and 1 psi. At that point, the main valve will shut, but the bypass is going to continue to flow, and it's going to continue to raise the pressure up downstream to 58 psi when the bypass shuts. So this is why it's so important to isolate the bypass when you're doing a test of the main valves. It will interfere with the readings. So if we go from static to that first 2 gallons a minute, so right now the bypass is open, but that main valve is shut. So now we're actually at the point just before the main valve opens. This is what it would look like with static flow if there was no bypass. So we've established that 1 psi differential across the second check, but both those 2 main checks are still closed. And then we go to full fire flow. Here we have the majority of the flow going through the main valve. You're still probably only getting a handful of gallons a minute through that little, 3/4 inch bypass. And we're at full fire flow, right? 15 psi pressure drop across the assembly. So let's move on to RPs. We'll go pretty quickly. So a reduced pressure zone assembly, it's an ASSE 1013 device, also known as an RP or an RPZ. The main difference between the RP and the DC is the relief valve. So you'll see them in a few different ways on this page, right? They're hanging down typically off the bottom of the valve. It is a differential pressure relief valve. It's built to detect a reversal in water pressure that would cause backflow, at which point it'll open and allow contaminated water to flow to drain rather than back into the drinking water system. So as a result of this safety feature, it's approved for use in health hazard applications. It also must be installed 12 inches above grade, so you shouldn't find these in meter boxes underground, and proper drainage should be installed to handle discharge from the relief valve. So let's take a little bit of a deeper dive into the hydraulics. So here's a cutaway of a large RPZ. You should note that instead of a 1 psi differential across the first check, it is a 5 psi differential. This creates the reduced pressure zone, so reduced pressure zone assembly. And that reduced pressure zone is between those 2 checks. The relief valve operates by sensing the differential across the first check. So supply pressure works to close the relief, and the pressure in the zone between the checks works to open it, along with a spring that creates the equivalent of a 2 psi at minimum. This means that if the differential drops to 2 psi, the relief valve opens. So I could talk at length about RPZs, but it's a little out of scope for today. So if you want to know more about how that relief valve operates and why they leak, I recommend you take a look at another ASPE CEU webinar I did on RPZs and mitigating their discharge to learn more. But for today, we're going to leave it at that. So here you have a smaller valve. So like a DC, the small valve, the big valve, they operate on the exact same principles, right? This is still a 5 psi check, a 1 psi check, and a 2 psi relief valve spring. So here's our detector assemblies, right? It's another ASSE number. This is ASSE 1047, also known as an RPDA. Very similar to an RP with the addition of that bypass for monitoring unauthorized water usage. Like the DCDA, these are primarily used in fire protection systems. You'll typically see these where there exists an additional hazard other than just static water. So anti-freeze in maybe an outdoor part of a fire sprinkler system or a foaming agent, any of those other additives, those will typically increase the hazard to where you would want to use an RPDA. In general, those are the rules. These are decided by AHJs. If you call me and ask me what valve should I use, I'm going to tell you to talk to them because ultimately they're the ones who have to approve it, and codes vary pretty widely across the country. So if we take a look inside one of these, here's another cutaway. Very similar to when we looked at the DCDA. So for purposes of this demonstration, I've increased that first check to the main valve to a 6 PSI differential in order to drive the first 2 gallons a minute through that bypass. Again, it looks like there's no differential across the second check, but that's because the downstream pressure has been affected by the lower overall pressure differential in the bypass. So if we look at those first 2 gallons a minute, now, just like when we looked at the DCDA, this is just at the point right before the main valve opens. So here we've established that 1 PSI pressure differential across the first check. Keep in mind that the second check. Keep in mind that second check is still closed. And we have that 6 PSI differential across the first check. And then we go to full fire flow. All right, everything is open. We're getting flow through the bypass and the main valve. We have, in this case, a 14 PSI pressure differential that we're seeing there. So we're looking at pretty high flow where most of the flow is going through that main valve. So here's what we're kind of getting into the meat of what we're talking about. So you notice that in order to drive the first 2 gallons per minute through the main valve in the assembly, we increase the pressure drop across one of the checks. So we need the main valve to open after the bypass, right? We can either decrease the strength of the checks in the bypass, or we can increase it in the main valve. Typically what's going to happen is you're going to increase it in the main valve because that bypass double check or that bypass RP, right, it's already been designed and engineered to be about as low as we can go. You won't find these leaving the factory at exactly 1 PSI per check because after a while, what will happen is hysteresis, right? Those springs get a little bit weaker. As they get worked, all of a sudden your valve starts failing its test. We don't want that, which is why you see it go out a little bit higher. Oh, I have a question. Is the drain connected to the bypass? That's what it looks like on the slide. I'm not 100% sure what you mean by that. Oh, no. Okay, yeah, that's a little confusing. No, so that's the sensing line. It actually would be plugged in right in line with the bypass, but on the other side of the valve, which is why it looks like that, but you can ignore that. Good question, though. Anyway, so we needed to increase the strength of the springs in the main valve to drive the first 2 gallons a minute through the bypass. This causes an overall increase in the pressure drop of the assembly. And of course, this is reflected in the flow curves. For those of you who aren't familiar, these graphs show the pressure drop across the valve over all of its flow rate. So here, the 6-inch RPDA versus the same style valve, but just an RP, has a full 2.5 PSI higher pressure drop at full fire flow. So this is also reflected in the allowable pressure drop by code. So here's our ASSE table of allowable pressure drop at rated flow. You're getting a full 2 PSI more allowed in a DCDA versus a DCA versus just a double check, and a 4 PSI more in an RPDA versus an RP. So this is a big difference, especially in fire applications, which is what these are being used in. So in fire applications, an engineer needs to prove, through hydraulic calculations, that the very furthest sprinkler head will get adequate flow if there's a fire. So a couple PSI could mean the difference between sizing a riser up or adding a booster pump, which is a lot of money to the customer. All right. A couple questions. So can I go back to slide explain? Okay, yeah, sure. So just a question about reading these flow diagrams. in this case, we've marked off two points. We have rated flow and like your typical flow. So that 1 star is 7.5 feet per second. That's your typical flow, and then we have a rated flow over at 1,000 gallons a minute. So you might see as many as 3 different points marked out, kind of a typical flow, rated flow, and UL rated flow, which would be even higher for a fire system. If you want to know more about that kind of stuff, I have another ASSE webinar on the basics of backflow when I go through how to read these flow diagrams. I also asked what a typical service life of a DCDA or RPDA. That depends largely on things like water chemistry. So if you have very aggressive water, which can mean either high chloramines, which tend to degrade rubber, or very low chloramines, which tend to exacerbate things like mic and corrosion, that can affect it, along with, is the valve stainless or is it ductile iron, or do you have a lot of debris in your water, or how often is this thing getting flowed? Typically, you see these things in service on the order of decades, but it varies very widely depending on the individual application. Basically, every backflow manufacturer will only warranty these things for a year. All right, so we see that we have 2 psi more allowed in DCDAs and 4 psi more allowed in the RPDAs. So that's quite a bit. So why is that? So let's dig into it. Essentially, the reason it's a fair amount higher is, one, we know we need to increase them, but we can't just increase the checks by, say, a 0.5 psi. And the reason is because these don't come out with precision values on the differential on each check. Ooh, bless you, somebody. So even though these valves, they hold very tight tolerances, little things with, say, the individual spring, where holes get drilled, profiles of seats can affect what these values are coming out of the factory. So let's go through a scenario. I have a double check valve, right? I have a main valve. I pull another smaller double check for my bypass. Each check is typically going to be about 1.5 to 2 psi. So if you're a tester, you should know it's typically around where you see each check in a DC. So I know I need to increase the pressure loss in my main valve to ensure the first 2 gallons a minute go through the bypass. The question is by how much? So if I imagine a worst case scenario, right? I have an off-the-shelf, say 6-inch valve. All of my tolerance stack-ups have given me two checks that are on the low end, so 2 1.5 psi checks for 3 psi. I choose a valve, say a 3/4 inch valve off the shelf for my bypass. All those stack-ups have given me one that's on the high end, 4 psi. So in order to increase my main valve by enough to ensure that even if I'm on the low end of those main checks, on the high end of the bypass checks, I need at least 1 psi minimum. Typically, I'm going to add even more than that, right, to really make sure, which is why those DCDAs are higher. How this gets accomplished varies widely from manufacturer to manufacturer. They might use an actual different spring. They might get shimmed somehow or twisted more. They might get pre-tested, so they might test checks individually and pick specific ones. It varies pretty widely, but either way, I need to add a fair amount to my pressure drop across that main double check. If I look at an RPDA, it's even more drastic. So if you've tested a lot of these valves, you've noticed that there's a much wider variance in that first check in an RP than there is in a first check in a DC. That's just because it's a higher value. Typically, when you look at things like spring manufacturers, they're going to rate it by a percentage of the overall strength. Because this is 5 times as strong, you get almost 5 times the variance. So in this case, I'm going to say it's between 6 and 8 psi, which is a pretty reasonable range that you would typically see in a first check in an RP. So again, I need to increase my pressure loss across that main valve. The question is how much? So again, what's my worst case scenario? So if I pull a main valve and it's already on the low end, so say 6 psi and 1.5 psi, I'm at 7.5 psi total. And I pull a bypass out on the high end, so an 8 psi and 2 psi. That's 10 psi. Now it's 2.5 psi to make up. You'll notice that that is the difference between the 6-inch RP and RPDA that we looked at the beginning. So the big difference between the standard valves and the detector assemblies here, you really see it in the RPDA. So 2.5 psi is quite a bit in a fire system. So now, new question, why type 2? So type 2 was created to respond directly to the fire protection industry's concern over the use of detector assemblies. So an ASSE Workgroup got together in 1999. Basically, ASSE knew that there were some current concerns from the fire industry. They brought a lot of people in. They brought fire protection engineers, fire protection, fire sprinkler contractors, and they asked them what their concerns were, and they highlighted 5 things: cost, size, ease of installation, pressure drop, and reliability after long static periods. As far as size and installation, that's been addressed by the industry. I'm pretty confident that since 1999, valves have continued to get smaller, they've continued to get lighter, they've continued to get easier to service. Reliability after long static periods was addressed with code with the actual ASSE test. So now there's a long static period test that makes sure that after that valve has been closed for a long time, it'll open when it's supposed to. But what we did with type 2 detectors is we addressed cost and pressure drop. So before I get into type 2, I'd like to do a survey. So Andrew, if you want to, oh, actually, you already did it. Look at that. So I'm looking at the survey. So we sent out, what is your experience with type 1 detector assemblies? Most people, 50% of the users, said they've installed, repaired, tested, or specified them. So that's quite a bit. If we will go on to type 2, it dropped to 37%. In fact, 22% said they have never heard of them. So earlier, I told you guys that these have been around for a decade. So in 2009, USD came out with their 10th edition, which described and gave standards for type 2 assemblies. Now they haven't caught on. The reason being is, in my opinion, from what I've seen and talked with people about, it's just that they're different. They're different. People weren't used to them. They see them in the field and they don't know what they're looking at, which is why I'm so glad you guys are here today, because we're gonna learn what these are, why they're different, are they approved? They are, and hopefully start popularizing these things because they were created in direct response to concerns from the fire protection industry. So let's see how. So what is a type 2? So here we have a cutaway of a large diameter type 2 DCDA. So what you'll notice is that the bypass starts after the first check. So we have our 60 psi, comes in, we have our first check clapper. Then in that zone, you see that bypass is coming up there on the top left, going through your meter, going through a single check, and coming in back in behind the second check. So let's look at a more basic diagram. So here's everything broken down nice and easy. You have your main valve, right? 2 1 psi checks. And you have your bypass, right? A meter and a single check. So many of you might be thinking, well, hey, those bypasses are cross-connection. Cross-connection should have backflow preventers. A single check is not a backflow preventer. This seems like it shouldn't have been approved. Well, let me tell you, we can think of this as two different backflows. One is your standard one, line size, right? So up there at the top, you have a single check, a big single check, and then another big single check. You have your 4 test cocks. But you can think of the bypass as a second backflow preventer that just gets sized down after the first check. So you might have a 4-inch first check, then you go down to a 3/4 inch bypass check. You have all of your test cocks where they're supposed to be. So what we're doing with this is we're putting the level of protection in the bypass of what we're bypassing. So in a typical type 1, you're bypassing an entire double check assembly. So you put an entire double check assembly in the bypass. In a type 2, you're only bypassing a single check, so you're only putting a single check in the bypass, but we're maintaining the same level of protection, which is the important thing. That's what we're all here to do, which is to protect our water supply through the use of backflow preventers. All right, so we looked at those. So here's our first 2 gallons a minute. So very similar to your DCDA type 1, except for in this case, your first check is opening up, your second check is staying closed, and then that first 2 gallons a minute is going to flow through this single check in the bypass. And then similar to your type 1s, at full flow, both checks are opening up. The majority of the flow is going through the main valve. So what happens when things are fouled, right? So now we have a rock taking the first check open. What's the level of protection? Well, you're still protected by a single check. If this were a type 1, you would also still be protected by a single check. We have the same level of protection. We have 2 checks there, so if the first check gets fouled, we still have a second check maintaining the integrity of that backflow. So we said that type 2 detectors addressed 2 things. Those 2 things were cost and pressure drop. So cost is the obvious one, right? So if you're installing a single check rather than a full double check assembly in the bypass, which one's going to be more inexpensive? It's going to be the single check. Now for pressure drop, the reason that the pressure drop is lower is because we're only dealing with the variation in a single check. So if we look on our right-hand side, in this case, I'm only thinking about the second check in that main valve and a single check in the bypass. So I look at my worst case scenario, I'm pulling, a low-end check, 1.5 PSI for my main valve, a high-end, 2 PSI for my bypass. My necessary increase to make sure that my flow goes to the bypass first is only 0.5 PSI. Basically, we've cut the tolerance stack up in half. So if we take a look at an RPDA2, the difference is even more significant. So if we look at a cutaway, again, where that bypass is coming in after the first check, it's going through a meter in a single check, and then coming back in after the second check in the main valve. So again, let's take a look at a simplified diagram. So here we have our differential pressure relief valve, our first check in our main valve, our second check in our main valve, and then our single bypass. So again, we can think of this as 2 different backflow preventers. One backflow preventer that's just the main line it's all line size. If it's 4-inch, you have 2 4-inch checks. If it's 6-inch, you have 2 6-inch checks. But then when I look at the bypass, we can again think of it just like a backflow that sizes down after the first check. So that reduced pressure zone and your differential pressure relief valve. Oh yeah, can you guys see that? That just got a question saying not seeing the diagrams you're talking about. Okay, I think it's just lagging a little bit, so I'll just give it some time.
Andrew's going to look into that issue.
Okay. So hopefully those will catch up. I'll just go a little bit slower with the slide changes. So that relief valve is still working in that assembly with the bypass. So I did get another question. Can RPDA be installed in the vertical? No, they cannot. In general, RPs cannot be installed vertically. There's one exception, the Watts LF909 in the 3/4 and 1-inch is approved by USC and ASSE to be installed vertically. That being said, if you do want to do that, you should consult whoever the authority having jurisdiction is, because sometimes they just say none. The reason for that is essentially that we want to make sure that if both checks are fouled and water gets past that second check, the first thing that it hits is the bypass. Typically the bypass is on the lowest point of the valve for that reason. Once you install it vertically, it can gravity feed directly past the relief valve and past the first check, which is why RPDAs and RPZs in general can only be installed horizontally. Ooh, I also saw a suggestion from Jeff, which is to say, make sure you close the survey pop-up if that's interfering. So.
Yeah, just when I send the results out, after you're done looking at that, you can just exit out around the top right there. You can see Cameron's slides again.
Great. So, same question. Is this safe? So if I have a fouled first check, is that relief valve still going to open? And the answer is yes. Right, so the relief valve is working for both the assembly that includes the bypass. So when we think of that as a backflow that sizes down after the first check, and it's working for the main valve. But if we look at the pressure drop, RPDAs is really where these make a big difference. So remember, we had a 2.5 PSI potential difference with the type 1 that we had to make up. With the type 2, we only have a 0.5 PSI, and that's because we're only looking at the second check, which has less variation. So if my worst case scenario, I have a main valve, second check on the low end, it's only 1.5 PSI. I have a bypass check on the high end, it's 2 PSI. I only have a 0.5 PSI to make up. So it gives me a full 2 PSI difference between an RPDA type 1 and RPDA type 2. So questions, there's our requisite dad joke for the morning. Why is it called a building if it's already built? So are they approved and how do they test them? So before I do this, I'd like to send out a poll. So Andrew, if you could send poll 2, which is about our survey forms. So your local test forms, if you're a tester, you might have more than one test form that you deal with. If you're not a tester, you don't know, you can answer D, but do they all include type 2? Do only some include type 2, or do none include type 2? I'll give you guys just a second to answer that. All right, so can even send results to audience.
Yep, I will in 2 seconds.
Okay, Greg will do that. So we're coming in mostly don't know, don't test. If we have a lot of engineers on the call, right? That makes sense since you guys aren't going to be out there testing. And then we have kind of a mix between all include the type 2, some include, and none include. So this is really common. A lot of municipalities haven't changed their testing forms in a very long time. And as a result, they haven't caught up with what is now a decade-old technology, having those type 2s on there. So let's address this, because one thing we see a lot of, and I think one of the reasons that type 2 hasn't caught on the way it really should have, is that if you're a tester and this wasn't covered in your testing course, and I can tell you it wasn't covered in mine when I got certified, and you walk up to these valves, you might fail it because you see a bypass, you see a single check in the bypass. In your head, you say there should be a full backflow preventer in it. You fail the test, and then we go through a whole thing where maybe it gets pulled out, maybe you end up calling someone like me, the manufacturer, another person has to get sent out. It's not great for anybody involved, right? Because the tester now has to deal with being corrected. The AHJ is getting phone calls. Maybe the engineer is getting phone calls. The customer has to get people out more than once. So getting the word out on these is very important because they exist for a reason. They have some great advantages to them. But people need to know what they're looking at when they go to test them. So first of all, how do you know if they're approved? Well, you know the same way that you would know for any other valve. You can check the nameplate, you can verify on the manufacturer's website, or you can verify on the approval agency's website. So if you look at here's, USC now has a great online approval list. If you go to their type selection, DCDA-2 and RPDA-2 have their own answers on that drop-down. And if you go to the ASSE Assemblies, right, it says that it covers reduced pressure detector assemblies type 1 and type 2 in that description of scope. So these are approved. You can go to the list, the USC list or the ASSE list, and look up your valve models, just like you would a normal one. The other thing is that these detector assemblies, that single check, it has a serial number and a model number, just like a full backflow assembly would, and you'll see that in the approved list as well. So testing, right? So different organization testing procedures cover type 2s. The software manufacturers that have the testing software and the submittal software have type 2 options now. Type 2s have serial numbers, one for the main valve, one for the bypass check, just like traditional detector assemblies, But always check with the authority having jurisdiction. Ultimately, it's always their call. But here's an example of a field test form that includes the type 2. So if you look at the DCDA, right, you have a checkbox for DC that contains check valve 1, check valve 2. You have a checkbox for DCDA that has check 1, check 2, and then bypass check 1 and check 2. Then you have a DCDA-2, which has check valve 1, check valve 2, and bypass check. What I tell people is, when in doubt, if you only have a form that covers your traditional DCDA, you already did the test for check valve 1. It was the check valve 1 of the main assembly. You can just copy that over. You're doing your job, but you already tested that check, and then you just go through your second check testing procedure with the single check and the bypass. On type 2, so I have a question. I don't understand how the first 2 gallons pass the bypass when both the bypass and the main assembly number 2 checks are the same pressure drop. Okay, that might have just been an issue with the numbers that I put up on the screen. The pressure drop across the main valve second check should be higher than the main valve, than the bypass single check. So when you're testing these, it's a good thing, even though oftentimes it's not part of the official procedure. When you're testing them, the second check should test higher than the bypass check. You can always do something like open up test cock number 4, let out, a gallon a minute of water, and make sure that that meter is running. Sometimes you do run into times when, say, if it is a special check, so often that second check in a type 2 DCDA will be a different check than in a regular double check. But often you can install a standard double check in there, right, because it's the same casting. People might put the wrong check in, then all of a sudden the first 2 gallons a minute is not going through the bypass. That's something you should flag with your AHJ. So speaking of which, so we looked at who used and tested type 1, who's used and tested at type 2, so we definitely have more people who are familiar with type 1, but actually more than I expected familiar with type 2, which is great to see. I have a final question, so Andrew, if we can do that third poll, which is just, do you record the meter reading? So is it recorded as part of testing? Do you just note if it's running, or do you not know? I expect based on the other ones, we're going to get a lot of answer C. But the reason I bring this up is a lot of municipalities, they require these detector assemblies, and they never read the meter. Reading the meter is very important because it should be important to your AHJ, because often your AHJ is the same company that's making the water. What they're using this meter for is tracking down that non-revenue water. Basically what they're trying to say is they want to account for every gallon of water that comes through, because they want to know, is it people stealing water? Is it leakage? Do they have to start looking for leaks in their water mains? They have to start looking for unauthorized connections. Those meters are there for a reason. People should be recording them. Oh, here's an interesting question. I cannot see type 2 in Watts Canada website. Are these not approved by AHJ? That would be by AHJ. They should be approved because they have all of the same certifications as your type 1s. So ASSE, USC, CSA, CUPC, CULUS. But I can always check with your, like all the large diameter FEBCO are type 2. But we can always check with your AHJ. I'm happy to have that conversation with them if they haven't encountered type 2s before. All right, guys. So it's interesting, most people don't know, but I'm glad to see that of the 22 users who recorded as part of testing or just note if it's running, 14 recorded as part of testing. That's great to see. I'm glad that those are being used. All right, so hopefully, our hour's getting to be just about up. Hopefully by now you understand the history, the necessity of the detector assemblies type 1 and type 2. You understand the hydraulics, how detector assemblies are different from standard assemblies, and how type 1 and type 2 detector assemblies are different. Get the benefits of the type 2 so you can now also walk up to one, assess if it's approved, check the websites, and understand how to test and report on them. So with that, if you have any other questions, please submit them. Otherwise, I'm going to pass this over to Greg.
Great. Thank you, Cameron. If you have any other questions, please type them in the ask a question box in the bottom left-hand of your screen. We'll take a few more minutes to address those. We did have one just come through now. Cameron, how does the AHJ decide what positive meter readings are from testing versus stealing the water?
Sure, that's a good question. I would say it depends on how they ask for the actual reading, right? Because the main thing that should be running that meter is the forward flow test for the fire. exactly when that meter gets read, if the backflow testing is part of the general fire protection testing, right, that can change up the procedures a little bit. But the gist of it is that if this thing is running constantly, you're going to get really high readings. If it's up 10 gallons, that could be just from typical testing. But if someone is stealing water or there's a real leak, right, over the course of the year at 2 gallons a minute for thousands of hours, you're going to see some pretty significant readings.
Are there any videos for how to test?
That's a great question. In general, I would say we as the manufacturers don't put out a lot of testing videos because we don't want to butt heads with AHJs. So, like I said, Watts, our headquarters in Massachusetts. In Massachusetts, we use NEWWA standards for testing. But if you're in Florida, you're using TRIO. That being said, there's probably testing videos out there, but I'm going to take a look into that. It's a good question, Mike.
We have a comment here. Some water departments even require meter readings before and after repairs.
Yeah, that's a good best practice for them. I know it's more work on the testers, but if the customers are paying for these detector assemblies, right, it's an added cost. If you're burdening the customer with that cost, then we should be using those meters.
Okay. Another question here. Do certain AHJs require type 1 over type 2? Seems like the benefits of type 2 outweigh the benefits of the type 1.
Sure, that's a great question. Some do. So I've run into AHJs where basically they haven't gotten a good explanation of the type 2 and how it's used, or they don't want to, it could be something as simple as they don't want to update their testing forms. But you do run into them, but after, in my experience, once you talk to them, once you talk to the testing schools, right, get it incorporated as part of the curriculum, they're willing to switch over because they do have some great benefits.
Okay, great. How are we going about getting the awareness, familiarity of the type 2 out there?
It's a great question. Things just like this. So I've given this presentation at several local ABPA meetings. So that's where all the AHJs attend. Typically, the people who are running the testing schools attend. For those of you who don't know, the ABPA is the American Backflow Prevention Association. If you do a lot of work with backflow preventers, I highly encourage you to get involved with them. You probably have a local chapter. They'll have local chapter meetings, and you'll be able to influence how these codes work, and then also just learn more about backflow prevention in general. So I always encourage people to get involved with ABPA on the local and national level. But I do a lot of these kinds of presentations. We have marketing literature out there, and more getting installed. So it's all about just reaching people like you guys. So thanks for being the tip of the spear with me.
Great. Those are all the questions we had come through today. So just want to thank Cameron, Andrew, and everyone else who joined us today. Just to let you guys know, a recording of this presentation and your CEU credit will be emailed to you. As you can see on your screen now, if you have any logistical type questions, you can reach out to me, gregory.jackman@wattswater.com, and any more backflow related questions, you can reach out to Cameron at cameron.rapport@wattswater.com.
Yep.
And finally, once this webinar ends, it's going to bring you to a page where you can choose to sign up for our next webinar in our WattsWorks Engineer Series on November 14th. It's called Commercial Rainwater Systems, Scale-Driven Designs. After that, we'll probably be continuing into next year with webinars in 2020. So that will probably be the last one for the year. You can also visit our on-demand webinars page, where you can watch the recordings of our past webinars in this series and take a quiz to earn more ASSE credits as well. And that also includes a recording of the cross-connection control and backflow prevention webinar we did with Cameron earlier in the year that he was talking about previously today. So that's all we got. Thank you again for everyone to joining us today, and enjoy the rest of your week.
All right. Thanks very much, guys.